Welcome. In this video lesson, we're going to take a look at some building blocks for vectors, specifically inner products, length, and orthogonality. It turns out that orthogonality is a very important concept, and essentially for vectors in 2 and 3 dimensions, this basically means that they're perpendicular. But it's better to use the term orthogonal since in higher dimensional systems, the notion of perpendicularity does not make sense because that assumes you can measure a 90-degree angle. But orthogonality is actually a useful concept. When you're doing a regression analysis, you want to do a linear regression or quadratic regression. That's based on orthogonality principles. And some very important things come to play there. And when we say higher dimensions, it doesn't mean that when we're outside of 3D that doesn't apply to the real world. In higher dimensions, we simply mean we have vectors that are longer than 3 components. So if you have 10 component vectors where those 10 components are some 10 measurements on people, then absolutely it makes sense to talk about higher dimensions. That would be a 10-dimensional space. So we'll start off with just a review of the idea of dot product. Sometimes this is also called an inner product in linear algebra. And the dot product between 2 vectors is a scalar value. It's a number that you get when you multiply 2 vectors, one that's on its side like this. So notice that this is a 1 by n vector. It has 1 row with n columns because we see that it goes from u1 to un. This one here goes from v1 to vn, but it has n rows and just 1 column. So when you multiply these two together dimensionally, inner dimensions match, and you get a 1 by 1 result. And the result is taken by multiplying the first component of the first vector with the first component of the second vector, and then all the way up to the last component of the first vector with the last component of the second vector. And you sum those results together. So here's an example where suppose we have 3 products that are sold in quantities of 10, 8, and 5. The respective prices are $5, $10, and $20. Use an inner product to find the total revenue. But what I want to do is I want to take 10 times $5, 10 units of product 1 times $5 per product 1, plus 8 times 10 plus 5 times 20, because I want to calculate the total across the board. So I can specify 2 vectors. I can say the first one will just contain the quantities 10, 8, and 5. And the second vector will contain the prices of each of those. And I'm going to omit units because we're just trying to calculate a number here. And so I should end up with total dollars. If I sell 10 units at $5 a pop, 10 units at $5 a pop, plus 8 units at $10 per unit, plus 5 units at $20 per unit. Let's see, I'll get $50 in revenue here, $80 in revenue here, $100 in revenue here, and that amounts to $230 of revenue. So that's an application of where we actually use dot product to solve problems. Now, it's also the case that when we compute the magnitude of a vector, we take the square root of the sum of the squared components. And this is due to Pythagorean theorem, at least in 2 dimensions, where if I have a vector in here and I want to, let's say that's the 1, 2 vector, and I want to figure out its length, I create a right triangle like this. This length here is 1, this length here is 2. This is the vector x. So then I could say that the length of vector x is equal to, by Pythagorean theorem, the length of x squared is equal to 1 squared plus 2 squared. So the magnitude of x is equal to the square root of 1 squared plus 2 squared. So we see that that's just the square root of the sum of the squared components of our vector. And in n dimensions, it's the same principle. So with respect to dot products, how this helps us is because I can express the length of a vector in terms of the dot product. So here we see that this is just the sum of the squared components. Well, if we think about what x1 squared is, that's just x1 times x1. And plus x2 times x2, all the way up to plus xn times xn. Now that's just a dot product that's already in expanded form. Just like here, this is already a dot product in expanded form. So if I put this back together as a dot product, I'll have x1, x2, all the way up to xn in my first vector, and x1, x2 all the way to xn in my second vector. And we see that this is really just vector x And it's the transpose of vector x, because if we think about a vector, usually we think about a column, and if you want that to specify that vector being on its side, then the transpose of it turns the column into a row. And dot that with the vector x, and you see that that's basically another way to compute the sum of the squared terms. And then the square root of that is, of course, gives us the magnitude. Another common way of writing out dot products, I don't know if I've mentioned it here yet, but sometimes rather than writing out, yeah, here it is. So this method up here, anyway, allows us to quickly compute the magnitude of a large vector without having to perform all of the manual squares and addition. So we could create vectors in a programming language and dot two vectors together, and it's one operation. It's one vector operation. Now in linear algebra, we write u transpose times v, just like we wrote here, to make sure the dimensions match. That, well, here we're taking a 1 by n times an n by 1. But a lot of times in classes like multivariable calculus, you just sort of omit the transpose, and it's just understood that if you write u dot v, that you're doing the dot product and that one of them is on its side. So it's totally acceptable to write it both ways. I prefer to specify transposes because unless you're specifically using the dot product function in like Python or something, then if you multiply two vectors together that are both, say, 3 by 1, you're going to get an error. But needless to say, if we interpret this as being the dot product, then all is good. So here are some properties of dot products. Dot products can take place either way. So if you think about why letter A is true, we need not go further than this example here. If we just commuted the 10 and the 5 and made this 5 times 10, 10 times 8, and 20 times 5, the 5, 10, 20 could have been in this vector, and the 10, 8, 5 could have been in this vector, and we would have come up with the same answer. So we would just be multiplying the terms or multiplying the factors in reverse order. Distributive property also, you can talk about the distributive property. You can distribute the vector in here. You can see that we're just taking w and back distributing it into the parentheses to make w times u, and u times w and v times w. But since multiplying dotting two vectors in reverse orders produces the same result, this would be the same thing as saying w dot u plus w dot v. Now notice also that this notation doesn't have the vector marks over it. The vectors are just bolded, so that's also a common convention. But when you write down a vector, you always want to put the vector hat over it to differentiate it from a scalar. You can see here we're using unbolded c to represent a scalar. And here we're just saying that if you scale a vector first and then dot it with something, that's the same answer you would get as if you dotted the two vectors first and then scaled it. So the constant, just like with matrix algebra, can be passed in between vectors and matrices. And u dot u is greater than or equal to 0, and u dot u is equal to 0 if and only if u is equal to the 0 vector. Okay, so if you dot a vector with itself, you're always going to get a positive number, or a non-negative anyway, because if you're multiplying the same component by the same component, you're essentially squaring the components, like here when you do x dot x. So squaring will always take away the signs. And the only way to get the dot product of 0 is if you're dealing with the 0 vector. So you'll see this lesson's kind of more bits and pieces of concepts. So here, let's say that you and your friend are at two different locations in two-dimensional space, and we want to know what's the distance between you and your friend, then find a general formula to express the distance between any two vectors, x and y. So here is a representation of our 1, 3 vector. So 1, 1, 2, 3. There's the 1, 3 vector. There is x. And then y is the vector 2, negative 1. So 2 and then negative 1 unit down here. And we want to know how far apart are these two vectors. So in order to be able to do that, we need to think about the distance between them as the distance between the two tips right here. And because this location right here is 1, 3, and this location here is 2, negative 1, we really can still form a right triangle out of this. And the way we could do that is by thinking about it like this. We could say, well, this is really a right triangle that looks kind of like so, where this unit right here is the difference between the x values. So the x value goes from a 1 to a 2, so this would have to be a length of 1. And then the drop goes from 3 to -1 in the y direction. That's a drop of 4 units. And now we could use Pythagorean theorem to do that. So another way to think about this, though, is that if we connect 3 vectors together, they're now established as being tip to tail. So if I think about this red vector here as, we'll give it another name, we'll call it z for the moment, then what's the relationship between x, y, and z? Well, they're all kind of tip to tail. Where z points, we'll just say z has its tip down here. You could draw it the other way as well, it wouldn't make a difference. But in this case, we could say that x plus z equals y, because we're doing tip to tail. X plus z equals y. And so that means I could re-express z in terms of x and y. I could say z is equal to y minus x. Now, since I want the length of z, that's equivalent to saying length of y minus x. So the length of y minus x is simply going to be, so that's the length of z by the equality is equal to the length of y minus x. And the length of y minus x is simply the length of the difference between the two vectors. So if that's going to be the difference between 2, -1 minus 1, 3, then you're going to see that the vector that we're actually measuring the length of is the vector 1, -4. And that's exactly what we have here, 1, -4. So to compute the length of that, that's just going to be the square root of 1 squared plus -4 squared. So in order to find that, we just have to subtract the two vectors and find their length that way. Another way you might see it written as, in general, you might see something like this. Or x, you could say, if this is, these components are called y and these components are called x, you could say y1 minus x1 squared plus y2 minus x2 squared, and so on, because we're taking the difference between them. So there's kind of our generalization of that formula. Now, another useful thing that we're going to need is in our bits and pieces analysis is the idea of a unit vector. So a unit vector is a vector that has length 1. Every vector can be scaled down or up to be exactly 1 unit long without changing its direction. So unit vectors are useful to work with since we will always know their magnitude to be 1. So let's think about how we would take the 3, 4 vector, which points not in the direction, or it's not a unit vector. In fact, its length is the square root of 3 squared plus 4 squared, which is the square root of 25. So this vector actually has length 5. All right, so 3 and 4 up will give me this vector here. And so its length is going to be 5 units long. So what do I have to do to something that's 5 units long? Let me draw that vector over off to the side, and let's think about this for a second. If this is 5 units long, then what I need to do in order to get 1 unit long pieces is I need to divide this into 5 segments. So 2, 3, 4, 5, right? And if I just take one of those segments, that vector right here still points in the same direction as the 3, 4 vector, but it has unit length. So what do we need to do to it? We need to divide it by its magnitude. So the unit vector is simply the vector itself divided by the length of that vector. Right? So that's essentially what we're doing here. So if I take 3, 4, and I take 1/5 of the 3, 4 vector, that's what we really mean by dividing by the length of that vector, we get 3/5 or 0.6, and we get 4/5, which is 0.8. And so just as a check to make sure that this works, we can take the length of that vector, so the square root of 0.6 squared plus 0.8 squared, is going to be 0.36 plus 0.64, which is the square root of 1, which is 1. So we've just figured out how to compute the unit vector. Now another thing that we often want to be able to do is to get the angle between two vectors. That's going to become a useful tool. So with these two vectors, suppose we have two vectors, call them x and y, that are given to us. We can call those components x1, x2, and y1, y2. And then we've already established that the vector that connects the two is just the difference between them, because if we go tip to tail, x plus y minus x has to equal y. Well, x plus y minus x is exactly y. And in order to find this angle, we realize that this doesn't have to be a right triangle. In fact, most of the time it's not going to be a right triangle. So none of these angles, even though this looks right, it may not be. And so we have to use law of cosines. Now, law of cosines looks kind of like Pythagorean theorem. You see the, like in this version of it, these are all equivalent versions. You don't need to tinker with all of them. It just is about how you label your sides. But little side c squared, which would normally be our hypotenuse, is still equal to side squared plus side squared. But because none of these angles are necessarily right, we have to subtract away 2 times the length of this side times the length of this side times the cosine of the angle c right here. Now when that angle is 90 degrees, cosine of 90 is 0, so this whole term goes away and you're left with Pythagorean theorem. Now, if we applied this law of cosines, but in terms of vectors, because we're dealing with vectors, not with just lengths themselves. So in order to determine the length of this guy, I'm just arbitrarily choosing this because I want to reference this angle right here. So notice that whatever length you have here is the same, or is the opposite, the side opposite to the angle that you want to measure. So cosine of c means we're hunting for c here. So we want this angle, therefore we want the magnitude of y minus x squared, and then we have cosine theta over here, equals the other side, length squared, plus the other side, length squared, minus 2 times the product of the lengths of the two sides, times cosine theta. Now we're not going to go through this algebra here. Check out the ebook on orthogonality if you want to see the derivation of this. But for in the interest of time, this is what we often refer to as the law of cosines for vectors. And after some algebra, you can reduce it to x transpose y equals the length of x times the length of y times cosine theta. So let's say we actually wanted to find the angle between us and our friend back here in the example, 1, 3, and 2, negative 1. Where are we here? 1, 3, and 2, negative 1. So to find that length, we have to identify one of these vectors as x and one of these vectors as y. So we had the 1, 3 vector, the 2, negative 1 vector, and what we wanted was this angle here. And so we created this non-right triangle. So let's call this our x vector right here. Let's call this our y vector right here. And to compute the angle, we have to take the transpose of x times y. And now we have to equate that to the length of x, which is the square root of 1 squared plus 3 squared. Multiply that by the length of y, which is the square root of 2 squared plus negative 1 squared, times the cosine of the theta that we're looking at. So when we compute the dot product here, we'll have 2 minus 3 is negative 1. This will come out to the square root of 10. This will come out to the square root of 5 times cosine of theta. And now if we divide both sides by the square root of 10 times the square root of 5, we get negative 1 over the square root of 50. You can multiply the radicands together, and now theta will be the inverse cosine of negative 1 over the square root of 50. And that comes out to about 98.1 degrees. So that is how we could find the angle, that relationship between the angle and the two vectors themselves. An important thing we want to consider is when will the dot product x transpose y be exactly 0 in this formula? So if we analyze this and we say, when will two vectors dot to be 0? Now these are two different vectors. When it's the same vector, the only way for that to happen is for the vector itself to be the 0 vector. But if I look at the cosine function as a function of theta, and I look at cosine theta, I know that it starts at 1, and then hits 0, and then -1, and then back to 0, and then back to 1. So the angle at which we hit exactly 0, because the length of two vectors, unless they're both the 0 vector, the product of their magnitudes will never be 0. If theta is equal to 90 degrees, however, we would have the cosine of 90 degrees, and that is equal to 0. And so this whole right-hand side would be 0. And so we could say that x transpose y equals 0 if the vectors are perpendicular. And the opposite holds true. If the vectors are perpendicular, then their dot product is 0 as well. We often say that these are orthogonal because, again, what does it mean to say perpendicular in 10 dimensions? You can't really measure angles, and when we say perpendicular, we mean that it has a 90-degree angle. But higher dimensional vectors could have dot products of 0. We'll still say that they're orthogonal. We won't say that they're perpendicular, but they share a lot of nice features like perpendicular vectors do. This is one of them. So like these two vectors, 3, 0 and 0, -2, for just some intuition, if we think about where these are, the 3, 0 vector points here. Oh, I'm sorry, no, that's the wrong vector. The 0, -2 vector points over here, and the 0, 3 vector points straight up. And we know that because the axes are perpendicular to one another, this is a right angle. But look at what happens to their dot product. If I dot 3, 0 with 0, -2, and the order in which I dot them does not matter. We have established that as one of the rules. 3 times 0 plus 0 times -2, which is 0. And so therefore, these vectors are perpendicular. And we can see it visually here as well. Now you can also have sets of orthogonal vectors. A set of vectors is said to be orthogonal if every pair of vectors is orthogonal. That is, for every pair of vectors, x and y, the dot product is 0. Furthermore, define a basis for a vector space Rn to be any set of n linearly independent vectors. A basis is a spanning set for Rn. That is, any vector in Rn can be created out of a linear combination of the n basis vectors. So basically what we mean here is that if we have 3 vectors, or rather in 2 dimensions, if we have 2 vectors, then as long as those vectors are not on the same line, then you can use multiples of them and tip-to-tail process to get anywhere you want, right? So they don't have to be perpendicular necessarily, but we could build a grid structure out of this to say, well, if I wanted to get to here, for example, then one thing I could do is to take this one far enough to where then I could take this one and shoot straight across, and I can figure out what scalars of each of those 2 vectors I have to add together to get there. So if you have a set of n linearly independent vectors, then you're going to be able to go anywhere you want in n dimensions. So is this an orthogonal set of vectors right here? Well, so we need to check whether every pair of vectors is perpendicular. So we have to check those 2, we have to check those 2, and we have to check these 2. So for 1, -1, 0 and -1, 1, 0, we would get -1 times 1 minus 1 times 1 plus 0 times 0, which is actually -2. So already the answer is no, because every pair has to be orthogonal. So you might say, but look at the next 2, -1, 1, 0 and 0, 0, 1. They have a dot product of 0, but it has to be the case that every pair has a dot product of 0, not just some, not just a couple. We could say that the last two vectors here are orthogonal to one another, but they are not orthogonal. They do not constitute an orthogonal set. Now, is this a basis for R3? Well, the way we find out is to do Gaussian elimination and say, is there any scalar multiple of these three vectors that can take me back to the point 0, 0, 0, that idea that basically if I have linearly dependent vectors, that with one vector I could leave, with another vector I could go somewhere else, but then the third vector will always allow me to come back. And these three vectors would represent a case where you have linear dependence. And that would not, these three vectors would together be linearly dependent. So if I reduce this, I would notice that if I added, I think I would get this. I think I would get 1, 0, 0, 0, 0, 0, 0, 0, whoops, 0, 0, 1, 0, and 0, 0, 0, 0. So this doesn't reduce to the identity matrix. That means that these vectors are linearly dependent. And in fact, you can see that if you take -1 times this vector here, you actually get this vector right here. So the second vector is a linear combination of the first vector. So they are not a basis, because I do not have three linearly independent vectors. So I need 3 linearly independent vectors. Okay, almost there. So if you do end up having a set of p vectors that are linearly independent, where p is less than n. So like here, we know that we have 2 linearly independent vectors. And how do we know that? Well, if you look at the vectors, if you look at the columns that are non-zero, that is, I should have said that whenever you look at each of the rows, and in the reduced row echelon form, any rows that have a 1 pivot in it, that corresponding column is a keeper, so to speak. So here we see that there's a 1 in the first column, so that means keep the first vector. In the second row, it's in the third column that we see a 1. So what that's going to tell us to do is to keep the third vector from the third original vector. And we see here that the middle vector, which in the third row we see is all zeros, there's no 1 in there. That basically means that the second vector is therefore can be created out of the other two. More specifically, if you take -1 times the first, you get exactly the second. So what we end up spanning then is we have less than n vectors. That is, we were working in 3 dimensions, but we only had 2 linearly independent vectors. So we say that in that case we span a subspace of Rn. So we can't span the entire space. We can't make it to anywhere within R3 with just those 2 vectors, but we can make it to anywhere that these 2 vectors 1, -1, 0 and 0, 0, 1 enable me to travel on. So if we look at where those are in 3-dimensional space, 1, -1, 0, if this is x, y, and z, 1 is this way, oops. 1 is this way. We'll just say that this is -1 is somewhere back here. And then 0, so this vector actually points into the xy plane. And then the vector 0, 0, 1 is the vector that points directly up the z-axis 1 unit. And so what we end up getting is we actually end up getting kind of a plane that we can create. And this continues to span infinitely far in both directions. But we can span anywhere along this plane, and that's our subspace that we can span with just the 2 linearly independent vectors that we have. So that's going to be an important concept as we move forward, is that if you have fewer linearly independent vectors in the dimension that you're in, then the size of the dimension itself, then you're only going to be able to travel within some region of that dimension. All right, we'll come back to that. We'll use that again. We're just kind of doing bits and pieces here. So an orthonormal set of vectors is an orthogonal set of vectors in which all vectors are also of unit length. The set in 6 is not orthonormal. How can you make it orthonormal? Well, first of all, this set 6 is not even an orthogonal set, so talking about making it orthonormal doesn't make sense. But basically, any orthonormal set, or any orthogonal set, we'll just write this, we'll say any orthogonal set of vectors can be normalized, meaning made to be unit length, by dividing each vector by its length. So that's no different than what we did earlier on, where we described how do you get the unit vector. We described up here that you multiply it by 1 over its length, or divide it by its length, and that gives you a vector that still points in the same direction, but that is 1 unit long. And now, the reason we're going to want orthonormal is that working with unit length, in addition to having the feature of orthogonality, is really, really, really useful. So let's take a look at number 8. We have an orthogonal set of vectors, and we know that if vectors are linearly independent, then the only way for this equation to be true for a linear combination of those vectors to equal 0, the 0 vector, is for all of the coefficients to be 0. In that case, those vectors would be linearly independent. But here's something interesting about what takes place whenever we take linearly independent vectors. We know that, when we take orthogonal vectors, we know that they are perpendicular to one another. So at least an intuitive way to justify this is consider 2 dimensions where you have 2 perpendicular vectors. Well, that means they point in different directions. One will allow you to travel along the axis that it points along, but to get off that axis, you actually have to use the other perpendicular vector. In 3 dimensions, the analogy holds as well. If you have 3 orthogonal vectors, now this is just an example, they don't all have to point along the axes, but here you can see that if they do, and these are perpendicular and these are perpendicular, that this vector that points along the z-axis, if you travel along it, you'll only be able to travel upward. If you ever want to travel, say to the right, then you would have to take this vector here, let's say that's a vector that points along the y-axis, so then you'll have to take that vector, and to be able to get out of that zy plane where those 2 vectors can take you, now you have to have a 3rd perpendicular vector to take you off there. So that's a little bit of the intuition behind it. Let's see why this is actually a super useful thing to have orthogonality. If you have an orthogonal basis for a space, u1 all the way up to un, and you want to write some vector as a linear combination of them. So now we have, they're all orthogonal. You have n orthogonal vectors in n dimensions. We know that they are going to be linearly independent, so you could generate any vector you want out of them. Now it turns out that to find C1, C2, and C1, normally we would build some sort of Gaussian matrix, and we would say, you know, here's your y vector equals C1 times this vector plus all the way up to Cn times this vector, and then we would form a Gaussian matrix and we would reduce it. But another way we can think about this is instead of having to go through all that energy, here's a little trick. If I just isolate myself to just 2 dimensions for now, C1 U2 plus C2 U2. So if U1 and U2 are orthogonal, that means they are linearly independent. And if I have 2 linearly independent vectors in 2 dimensions, I can span anywhere I want. I can get anywhere I want. Suppose I want to get to the vector y. So I have my 2, say, orthogonal vectors. And just to emphasize that they don't have to point along the axes, they could be perpendicular like this. To find, or to figure out how to get to some other vector, say y, that's over here, well, you know, if I take this vector backwards and maybe, let's pick a different vector slightly, maybe it points that way, if I take the right combination of these two vectors, I can get to the tip of y pretty easily. Now, since u1 and u2 are orthogonal to one another, I can perform this little trick. If I multiply both sides by u1, for example, here's what happens. If I multiply u1 on the left and u1 on the right, I will actually now distribute the u1, so I'll have c1 u1 times u1, or dotted with u1, plus c2 u1 dotted with u2. And remember, we don't have to do the transpose. It's kind of convenient not to have to do that. We just put the dot in between them. Now, because u1 and u2 are orthogonal to one another, this is 0 right here. And so our equation reduces to u1 times y, or dotted with y, equals c1 u1 dotted with u1. Well, that allows me to really easily solve for c1. c1 is going to equal, since this is a scalar and this is a scalar, I'm just going to divide both sides by u1 dotted with u1. So u1 dotted with y divided by u1 dotted with u1. So this tells us how we could find the c1 coefficient. All we need to know is, what is our u1 vector? Well, that's going to be given to us because we're saying given an orthogonal basis. And all I need to also know is y. And since the order in which you take the dot product doesn't matter, each of these coefficients, ci, is just going to be y dotted with the particular u corresponding to that same index. So if we had c3, this would be y dot u3 over u3 dot u3. So this is a fast way to compute those coefficients without having to do any Gaussian elimination.